Math 1343, hypothesis test, population proportions, testing one population proportion, the critical value approach. In the previous videos, we've kind of discussed the generalities of hypothesis tests, and I tried to keep the videos relatively short. I do realize the very first one hit 17 minutes. I don't expect this one to be short because I'm going to attempt to do two things. Number one, review how to do the critical value approach, and number two, actually do an example while reviewing. So I do expect this video to take longer than I normally would, but following this, we'll do another example where I can show you that it doesn't really take that long to do a hypothesis test. So let's take a look at this situation. A school claims each year 30% of its students park on campus. A survey of 50 students shows 20 park on campus. Test at alpha equals 5% if the proportion of students who park on campus is different than 30%. You can tell we have the makings of a hypothesis test for a variety of reasons. Number one, we're point blank told to test something. That's a dead giveaway. Number two, we're given a significance level of alpha equals 5%. But thirdly, in a broader perspective, we have a claim about a population and we have a sample that disagrees with that claim. And it may not be obvious that the sample disagrees with it yet, but if you can check 20 out of 50, that's 40%, as we'll see here in a moment. All right, so how are we going to do this? And how are we going to do this using the critical value approach? Well, there's actually 4 steps to conducting a hypothesis test using the critical value approach, but I will be putting a 5th step in the perspective of this being a word problem. But the first step for any hypothesis test is to state the hypotheses. After all, at the end, we're going to make a judgment call, a decision about the null hypothesis, so it would help to know what it is. And we also need the alternative hypothesis because that will help us determine if this is a left tail, right tail, or two-tail test. All right, so step 1. When you state your hypotheses, you will always have an H0 and an HA, or depending upon the textbook or professor that you have, this might be H1. But remember, these aren't variables. You don't set them equal to anything. They are simply abbreviations for the phrases null hypothesis, alternative hypothesis. So what are we claiming? We're claiming that 30% of a population has a characteristic. In this case, the population of all students at this college, at this school. Well, percent is a proportion. So we are making a claim about population proportion whose variable is p. Our claim is that p is equal to 30%, or as a decimal, 0.30. But what's our alternative hypothesis? Well, if you look at the last sentence, we're being asked to test if the proportion is different than 30%. The phrase is different than is a phrase to indicate the symbol not equal to. So our alternative hypothesis will be p is not equal to 30%. You claim it's 30%, we have a sample that says it's not, and the battle is on. Now, before we move to step 2, I do want to remind you that the alternative hypothesis does dictate whether this is a left tail, right tail, or two-tail test based on the relation between the parameter and the value. In this case, when the alternative hypothesis includes is not equal to, that means we are going to do a two-tail test. Which takes me to step 2. Step 2 is to sketch the rejection, and there's a dash after rejection, and non-rejection regions. Determine the z-score, separating them. These z-scores will be called z-scores, excuse me. There may be two of them, depending upon how many tails there are. But these z-scores are called your critical values. Hence the name critical value approach. All right, so we draw a picture. Now, how do we draw this picture? Well, first you draw a bell curve. Then, according to the alternative hypothesis, you shade in the left, right, or two tails. Since this is a two-tail test, we're going to shade in two tails, the left and the right. Now, in the context of hypothesis testing, whatever tail or tails you shade in are called the rejection regions, which I will abbreviate RR, henceforth. This bell curve has two rejection regions since it was a two-tail test. The middle will be the non-rejection region, which I will abbreviate in RR. And what's going on here is we're setting up a picture, and we're going to see where our sample lands in this picture. If our sample ends up landing in the non-rejection region, then at the end we will not reject the null hypothesis. Sure, our sample deviated from the middle, just not far enough. But if it does deviate from the middle far enough and go into either of the rejection regions, then we're going to reject the null hypothesis at the end. Now, to complete the second step, we need to figure out the boundaries that separate these regions. When you're testing a population proportion, you are going to use a z-score. It won't always be a z-score, but when you're testing a proportion, it is. When you're testing a mean, it'll be a t-score. But we need z's. And in order to find these z's, we need to know some areas, but this is where the significance level comes into play. Recall that the significance level is the tolerable probability of making a type 1 error. But in the context of this flow, and this is probably more important, the significance level will always represent the area of the rejection regions. Always, always, always. And since there are two rejection regions, a left tail and a right tail, we have to take that 5% and split it amongst the two tails. So we know that each of these areas will be half of 5%, which is 2%, and as a decimal, 0.025. Because of the symmetry of the standard normal distribution, I know these z's are going to be opposites, so we really only need to look up one of them and then change its sign for the other one. Keeping in mind that your z-chart works with left areas, I'm going to look up the left z, or rather I would if I had a z-chart in front of me. But I invite you to get out a z-chart, find an area of 0.025. Remember that the areas in the z-chart have 4 decimals, so we could put a 0 there. But if you look that up in a z-chart, it should be exactly in there when z is negative 1.96. And because of the symmetry, the other z is positive 1.96. Again, these two numbers are called critical values. They're the z-scores that separate rejection from non-rejection. Basically, they're the z's beyond which, if our sample lands in either tail, and excuse me, this is 1.96, not 6.9. A little bit of temporary dyslexia there. But the critical values separate where we will make our decision about rejection or not rejecting the null hypothesis. But in order to do that, we have to figure out what our sample tells us and where it would land along the spectrum. And that's step 3, which I'm going to write here. Step 3 is to calculate the test statistic. Numerically, a statistic is always a measurement from a sample. Parameter is a measurement from a population. Statistic is a measurement from a sample. Just remember the alliteration and you'll never forget that. Parameter, population, statistic, sample. But to calculate the test statistic basically means what did our sample give us, and let's compare it to this. But in order to do that, we'll have to convert it to a z. Now, this move is a formula move, assuming that you're not just using technology that says, bam, here's your test statistic. And such technology does exist. In the context of testing one population proportion, the formula for calculating the test statistic will look a little familiar from what we saw when we were doing a confidence interval for one proportion. The formula for the test statistic is Z is equal to P hat minus P naught, a P subscripted with a 0, I'll elaborate in a moment, divided by the standard error, where the standard error is the square root of a fraction. The numerator is P hat. No, it's not. Sorry. The numerator is P naught, P subscripted with a 0, times 1 minus P naught, all over n, the sample size. So this formula for the standard error looks like the same one when we did a confidence interval for estimating one population proportion. The main difference is, back then, this was a P hat, this is a P naught. Now what does that subscript of 0 mean on the P? Well, let's elaborate. P naught is the hypothesized value of P. Hypothesized value of P. And the reason it's subscripted with a naught is because you get its value from the null hypothesis. So in this case, it's 0.30. Now, also we need the P hat, which we don't have yet, but we were given the ingredients to calculate it. Remember that P hat means the percent of a sample that is characteristic. In this case, it could be 20 out of 50. So at some point, we're going to need to calculate the P hat, but let's go ahead and calculate the standard error. Our standard error is going to be the square root of the hypothesized value of P, which was 30%, 0.30, times 1 minus that. Well, 100% minus 30% is 70%, so 0.70, over the sample size, which was 50. We surveyed 50 students. This goes into a calculator, and using my standard procedure, we will just assume if it does not round out to 4 decimal places, that will round it to 4 decimal places, and let's see what we get. My advice for doing this is to figure out the fraction first and then square root that answer. 0.30 times 0.70 divided by 50 equals a number, and if I square root that to 4 decimal places, I get 0.0648. But that's not my test statistic. My test statistic is something to compare to these Z's, so I need to calculate this Z. But we need to know P hat, so let's figure out that. Well, 20 out of 50 students parked on campus, 20 out of 50 is 40%, or 0.40. And so my test statistic, Z, is going to be what I got from my sample, which was 40%, minus what I'm claiming from the null hypothesis, which was 30%, 0.30. And that's going to get divided by the standard error, 0.0648. And we'll round this off to 4 decimal places, divided by 0.0648. And we get 1.5432. It's like we're counting down, 5, 4, 3, 2. All right, so this is our test statistic. In other words, this is the z-score associated with what we got from our sample. Test statistic. Now, we still got a couple more steps. Well, one as part of the hypothesis test, and one as part of this particular word problem. But, sorry folks, I was looking for something and I don't see it. That's okay. But those 2 steps don't take up much room at all. In fact, I think I have room on the bottom of that list over there to write them. Yep, I do. Step 4 is simply make a decision. And to be a little bit more specific, make a decision about the null hypothesis, and I guess I can just write that as H0. So we're going to make a decision about the null hypothesis. And as was mentioned in the 2 videos ago, when we make a decision about the null hypothesis, there's only one of two things we say. We reject it or we don't reject it. Now, how do you make this decision? This is where everything comes together. Your decision is made based on where your test statistic, which I'm going to put an asterisk here, lands relative to your critical values. 1.5432 is to the right of 0, but not quite to 1.96. So I'm going to put that asterisk here. Now, is it precisely there? Probably not. But relative to this critical value and this critical value, it is in the correct place. It's positive, but it's not quite as large as 1.96, so it would land right about here in the non-rejection region. Based on where your test statistic lands relative to your critical values, you only say one of two things: reject the null hypothesis or do not reject it. Since I am in the non-rejection region, my fourth step is to simply say, do not reject the null hypothesis. Yes, our sample deviated from our population claim, which I literally just erased, but it didn't deviate enough to say our claim was wrong. When this happens, we basically say, well, the reason it disagreed is because of the particular sample that we picked, not because our population claim was incorrect. So that's step 4. Make a decision about the null hypothesis. Again, that's one of two things: reject the null or do not reject the null. In this case, non-rejection region means do not reject the null. Now, as a hypothesis test, it's over. But as a word problem, it requires a little bit more analysis. And honestly, I should have actually ended this problem with a question, and I do have a little space here, so I'm going to go back and fit a question in there. Can we conclude that the proportion, those words are fairly interchangeable. Can we conclude that the proportion of students who park on campus is different than 30%? I can't quite fit it in that one line, so I'll make do here. Can we conclude that the proportion of students who park on campus is different, if I can spell, than 30%? And again, sorry I'm squeezing in that little space there, but we're almost at the end. Your 5th step, and this is when you think of this not just as a statistics problem in theory, but in application relative to the word problem, your 5th step is to answer the question. And I know that may sound kind of obvious, but you'd be surprised how many people, when I test this, will go through the first 4 steps of the hypothesis test and never bother to answer the question at the end. I'm going to restore the hypotheses just for a moment. They're the same ones that were up here a moment ago. Because when you go to answer the question, in this case, can we conclude that the proportion of students who park on campus is different than 30%? This is really asking, can you conclude one of the hypotheses? So in order to answer the question, you have to ask yourself, which hypotheses are you asking can I conclude? And what was my decision about the null? When you make the decision about the null, do not reject or reject, you're basically saying, I'm going to go with this hypothesis and not the other one. When I say do not reject the null, that means I'm keeping it. And if I'm keeping it, that means I have to reject the alternative. Now, that doesn't mean the null is true and the alternative is false. That means based on our evidence, this is what we would conclude. But as far as the question, can we conclude that the proportion of students who park on campus is different than 30%? What we're basically being asked is, can we conclude, well, which hypothesis says that the proportion is different than 30%? The alternative. So to rephrase the question in the context of hypotheses, we're being asked, can we conclude the alternative hypothesis? And the answer is no. So how would you answer this? Well, basically you just say yes or no and then restate the question. No, comma, we cannot conclude. And then the rest of it. The proportion of students We cannot conclude the proportion of students who park on campus is different than 30%. Sometimes it takes longer to write the answer than to do the problem. But again, doing the problem is just a matter of getting acclimated to the steps. State the hypotheses. What are you claiming? What are we counterclaiming? Sketch the regions. Based on our alternative, is it left tail, right tail, two tail? Based on that plus the significance level, what z-scores separate the rejection region from the non-rejection region? Calculate the test statistic. Translation. Use formulas to convert what our sample told us into a z-value that we can compare to the critical values. Make a decision about the null, which is always reject or do not reject based on where your test statistic lands relative to the critical values. And then finally answer the question. And remember, when you answer the question, focus on which hypothesis are we accepting and rejecting based on our decision, and which hypothesis are they asking that we can conclude. So I can't always say when you reject the answer is yes, when you don't reject the answer is no. It just depends upon your decision and what the question is asking you about. In the next video, we're going to do one more hypothesis test, but without explaining and justifying all the individual steps. We're just going to go through it because I want to show you how quick these problems can be. And I may have just set a record for the longest video I've ever made.